to talk about, more lights. Okay, I'm going to talk about transformers and graph neural networks. So it's best, whoop. Careful. Okay. What I was saying, yes, I'm going to talk about transformers. So you know transformer is a revolutionary technique for natural language processing. And this is something that works very well when you are in this large-scale regime of data. So if you're able to scrap internet, suddenly you are able to make incredible prediction in language. So you know very well about this. The thing with transformer is it needs to have a very large-scale data set, training set, to be working well. Okay. So you know inside the transformer there is this attention mechanism. The attention mechanism is basically an adjacency matrix of a graph. Okay. So this is something which is completely dynamic. So you receive a sequence, and dynamically is going to have the connection between words, which make sense in the context. Okay. So transformer basically is the ultimate architecture today if you are in this large-scale regime. Okay. If you are not in the large-scale regime, and this is what happened in AI for science, in biology, in physics, in chemistry, then you need inductive biases to compensate from the lack of large-scale data set. And today, one of the most powerful inductive bias is graph. Okay? So if you take a molecule, you have atoms, they are the nodes of your graph, and then you have connection, which are the edges between the nodes. So this gives you a powerful way to predict property from physics, chemistry, biology, and so on. Okay. So what we did, so when we saw the emergence of transformer, and when we look at the, I'm going to show you the history of GNNs, we saw that eventually the two are going to merge. So the question is how mathematically we are going to make, this unification between transformer and between graph neural networks. So this is the what I'm going to tell you now. So first thing, what I'm going to do is to make a very quick review of graph neural network. So we started graph neural networks 2014, 13, and I'm going to show you the evolution, how we get from the original transformer, the original graph neural network that was designed based on convolution, and now more recently designed on attention mechanism. Okay. I'm going to talk about something which is very important because graphs, they are very general. Okay, you can find graph in many applications, and you can apply graph neural networks. The problem is it's not going to work because graph, it's not like an image. An image has orientation. You have up, down, left, and right. This gives you a lot of good information. Where is your pixel in your image? In graph, we don't have this. For arbitrary graph, we don't know where is the center of the graph. We don't know where is up, down, left, and right. Okay? So we miss basically the position of nodes. And this is very important if you want to increase the expressivity of your model, so the class of functions you can represent. So there has been ways to do that, and I'm going to show you what we did with graph positional encoding. Okay. I'm going to go very quickly on the transformer, regular transformers, and then I will introduce graph transformers. The next thing we did is to generalization. So the question is, okay, if you are in biology, your graphs are usually very small. 100 nodes, 200 nodes, and not more. The question is how you do when you have millions of nodes. Okay. So you need to introduce some hierarchical property. For example, you want to cluster similar nodes and get a supernode. Okay, and you apply again your graph transformer. So this is the last part. Okay. Okay. So yesterday, what I observed is that. So I know very well. Sorry, I know very well the material. It's available online and everything. But you guys yesterday you asked a lot of questions to the speakers. So let's make this, also quite interactive. So if you have any question, not at the end. Because again, I know well the material, but during the presentation, let me know. Okay, I will of course have time for the question at the end. We can also during lunch we can talk about this. But if you have any question during the time, I think this is why we have this winter school. right? So we have more interaction than just, you can go on YouTube and you can find my, my presentations. All right, so the review of graph neural networks. So deep learning is very good if you have these three ingredients coming together. So basically, large-scale data set, a lot of GPUs, and a good neural network. Okay. So there are today 4 classes of neural networks: convolutional neural networks, recurrent neural networks, transformers. And these 3 classes, they work very well when you have grids, sequences, and sets. Okay. So for an image, basically what you have a grid that is going to support your features, your color features, right? So you can see that. For text, you have a sequence of discrete variables, which are the words, okay? And for speech, you have a 1D sequence, and each node is basically the air pressure, okay? So these 3 classes of neural networks, they are, in some sense, satisfying these 3 conditions very, very well. Okay, you can get a large data set, you can get a good neural network, and you can get a lot of GPUs. And basically, there are some professional library like PyTorch or TensorFlow that was developed precisely to leverage as much as possible the hardware, the GPU hardware. So it works very, very well. Okay. Now we have these graph neural networks, which is more universal, more applicable to different applications than transformers, but they are not optimized. And the problem is the hardware. Okay. So we don't have today a GPU which is very fast for sparse linear algebra operations. Okay. So this is one of the ingredients that is missing. Okay. So this is also maybe one of the reasons that this is not well adopted in industry. Okay. So what's a graph neural network? So this is basically a parametric function, and the parameters are the weights that you are going to find by backpropagation. Okay. And this function is equivariant with respect to the node ordering. Okay. So if you have a graph, you have nodes. These nodes will have an index, 0, 1, 2, 3. So they will be stored on your computer, okay, with a specific address. If you copy paste your graph, you're going to have a new indexing of your nodes, but you still want your node feature, your edge feature, your graph feature to be the same. Okay. So what you want is basically operations that is going to preserve the features if you change the node indexing. Okay. So this is called equivariance with respect to parametrization. Okay, of the graph. So a message passing, graph neural network is also called a message passing. It has 2 operations. It's basically a node update. So you see that this is a graph here at layer L, and this is the next layer, L plus 1. So this is the node I. It has some node feature, HIL. And I'm going to basically to use this node and the neighbors, and also maybe the edge feature, to update the vector at the next layer. And I'm going to use a very simple operation, which is basically something that is going to apply on my node and also the neighbors, okay, that you can see here. The other operation that I have is the edge feature. Edge features are very important for some application, for example, for protein folding. So you know the AlphaFold, Nobel Prize in chemistry, so or biology, I don't remember now. Basically, what he's trying to do is, so he has a sequence of amino acids, and then he's trying to find the 3D structure, which is basically the pairwise distance between all amino acids in 3D, in the 3D world. Okay? So this is the edge feature. Your edge feature are the pairwise distance. So if your system, for example, AlphaFold, was not equipped with this edge feature, it will not be able to be as expressive and predict very well the 3D representation. So the edge feature also depends basically on the edge feature you have here at the layer L. It also depends on the node feature of I and J, which form the edge. Okay. So basically, the number of papers of graph neural network is the number of functions here you can imagine. Okay, so today, I don't know, we have maybe 20,000, maybe more papers. So people decide to have a new node function or new edge function, and they write a paper and they publish. Okay. So here I'm going to tell you a little bit about the history of graph neural network. So everything starting in 2009 in Italy. And then it was, so this is when I started working on that. It was in 2014 and 17, and it was basically after the revolution of deep learning in computer vision. So you know in 2012, there was ImageNet competition, and suddenly the performance was as good as any human. Okay? And it started the deep learning revolution. So 2012. So a bit later, what happened is that I was working on graph theory for different applications. And then there was Jan LeCun. He was at Facebook, just hired at Facebook. And of course, he was pushing to do convolutional neural network on graph. Okay. So at that time, I was working on the math of this, nothing to do with deep learning. But then he was very quick to understand that we can do the connection. So this is the spectral GNNs that I'm going to talk about. Then later, we improved the expressivity by using the direction, the one I spoke at the beginning. Then there was very theoretical GNNs, which was called Westphaler-Lehmann GNNs. I'm going to talk a little bit about this. And finally, I think we are now in this time of graph transformer. And yeah, so idea is, of course, you want something more expressivity. Expressivity is not enough. You need also generalization, which is much more complex. And you want something to be linear in terms of complexity. Otherwise, you will not be able to make a product of that. Okay. So the vanilla GNN started in 2009. So it was Italian people. I didn't know about this actually until 2016 or 17, I don't remember. But what was interesting is that they already understood everything mathematically to do a graph neural network. Everything was there. Okay. So they had the equivariance with respect to the index permutation. They were independent with respect to the number of neighbors, the graph size. They had the local reception field. So you know about the local reception field? Yes, some of you? Why local reception fields are important? What's the inductive bias coming from the local reception field at each layer when you stack multiple layers? Okay, take a paper. We're going to make an exam. I'm kidding. So if you have a local reception field and you stack many of them, what you're going to learn is basically a multi-scale, a multi-resolution representation of your data. And they are very important because the world is basically multi-resolution. So an image is composed, for example, we have the edges. Then you can compose maybe one eye. Then you compose two eyes. Then you compose with the mouth and then with the face. This is a hierarchical representation of your data. And it's very, very powerful. Okay, so when they develop convolutional neural network, they have this max pooling operation. And this is precisely the, where you get this multi-resolution. Okay, so where do we get that with attention? Okay, I'm back to school now. So where do we get back with attention? Do you think attention neural network, so the transformer, is hierarchical? Yes? Or no? It is actually. So you know I don't know if you already have some lecture on transformer before. So you know what transformer is doing is basically it's a convolution. It's just the convolution is going to capture maybe a tree consecutive words. Okay. What the attention is doing is that it's going to capture three important words which are connected to the query word that you want. Okay, so if you have a sequence, instead of having three consecutive words, you're going to have three words which are not consecutive, but which are important relative to the prediction you want to do. Okay, and then this is just one layer. Then you go to the next layer. You still are going to do a sparse connection between this word and maybe 3 or 4 other words. Why I say three or four? Because you are using softmax. So even if you apply softmax on a sequence of 1,000 words, it will only output maybe 4 non-zero because of the sparsity, the exponential. Okay? So if you stack many of that, you will get a hierarchical representation of your text. Does it make sense? Yes? Okay. So basically, we have the local restriction field because in graph, we only look at the neighbors, and that's it. That's the only thing we do. So if you stack many layers, you will learn basically a hierarchical representation. Weight sharing, each time your weight is going to be the same. So this is the pattern matching in this process. So you have your W, you have your vector HI, you do WHI, so this is a just pattern matching, right? You have the row of your W times H vector. So you just do pattern matching, that's the only thing you do. But you do that at each node on your graph. So this is equivalent to which operation? Convolution, thank you. Convolution. Yes, so it's a very weak convolution, but it is, okay? And you still have the linear complexity, number of nodes and number of edges, okay? So the first model of GNN that was defined in this paper, if you know recurrent neural network, this is the same. Okay, so recurrent neural network, so this is a new word, XI. You have the memory of the sequence so far, which is HJ. Do you know recurrent neural network, by the way? Thank you. Okay, so you know what recurrent neural networks do. Basically, you have a sequence. At each word, this representation, this embedding representation, is going to summarize everything before. Okay, so he has a summary of everything before. He gets a new word, and then he's going to predict the next word using what happened before plus the new word. This is what he does, right? Here you have exactly this operation. This is the new word, and this is the summary of what happened before. The only difference is for recurrent neural network, it's a sequence of what happened before. Here, it's a graph. Okay, so you may not have a sequence, you may have a tree, for example, of what happened before, but this is also some kind of summary. Does it make sense? Yes, thank you. All right, so, okay, nice. Mathematically, it works, right? This is the first graph neural network. Mathematically, it is fine. So why it doesn't work in practice? So what's the most important limitation of recurrent neural network? Why is not today everything is not RNN? Why is everything is transformer? Yes, the vanishing gradient problem. So the problem with this stuff is basically, so each time you update, you're going to summarize, you know, the sequence. At the beginning, the sequence is small, maybe 1 or 2 words, but then the sequence is going to increase, 10 words, 100 words, 1 million words. The problem is that you cannot summarize everything in one vector, okay? Because what will happen by backpropagation, it will have a lot of decreasing information coming from the nonlinearity. Okay, so when Google Translate in 2017 decided to go to RNN before transformer, basically they have only 3 layers of RNN and not 100 because of the vanishing gradient problem. Okay? All right, so what we did in 2013 and 16, so the first paper was by Yann LeCun and Arthur Slam. So basically they say, okay, convolution, neural network for images, okay, fine. Now let's do it for graph. The problem of graph is this is not homogeneous like a grid. Okay, a grid is a regular lattice. You know, again, where is the center, where is up, down, left, and right. You know everything, okay? I'm losing someone, okay. Should I go more high level? High level, okay, you don't want to go to the details. You want details or you want just high level? Okay, let me know because I need to adapt. If everyone leaves, I know it's soon lunch, but if everyone leaves before, I will be sad. Okay, so what happened? So you do convolution on grid, and everything is very well defined. Okay, so you probably know fast Fourier transform, FFT, and log n complexity. Okay, so you can do, you know, mathematically it's well posed, only one solution, and the implementation is great. This is very well on GPU, so everything is fine. The problem when you go from regular grid to irregular grid, for example, if you have, this is a knowledge graph, this is a transportation map, this is a molecule, meshes, you don't have anymore this nice regularity. You cannot use this anymore, okay? So the question is, okay, you can mathematically define, so the convolution can be defined in two ways, right? You can do it in a spatial domain, and I'm going back in the next slide on this, or you can do it in the spectral domain, okay? So the convolution between two signals is basically you do the Fourier transform of the first signal, Fourier transform of the second signal, so you are in the Fourier space, you pointwise multiply, okay, and then you do the inverse Fourier transform to go back. All right, so mathematically, this is well posed, and this is clean, okay? There is no bad things. The problem doing that is there are, for example, the complexity. The complexity is going to be n cubed. Okay, so this is very bad. There is also some problems of stability. But you can solve all these problems actually using some technique that we based on. I don't have time to go too much into the detail, but so let's say, yeah, maybe let's go just here. So you have the convolution between your patterns, okay, that you are going to learn by backpropagation, and your signal, okay? And then you're going to apply a nonlinear activation, okay, to get to the next layer. This can be rewritten on, so you have so U is the matrix of eigenvector of your graph. So your graph is a matrix, right? So you know that if you have n nodes, you have n nodes here, n nodes here. You look at the connection between the nodes. You do exponential of the connection, and then you have an adjacency matrix, okay? So this represents a graph. If you do a matrix factorization by doing, by doing the eigen decomposition, so you're going to have a matrix of n eigenvectors, okay? And then you're going to have a matrix, a diagonal matrix of n eigenvalues. Eigenvectors represent basically the oscillation of your domain, okay? And the eigenvalue represent basically the frequency, how fast they oscillate, okay? So now to do the convolution, you just need to apply a spectral function. Some of you have done signal processing. Perfect. So you know in signal processing, for example, you have an image and you have noise, and you want to remove the noise. So you know the noise are actually the high frequency part of your image. So what you do is that you design a filter in the frequency space, in the Fourier space, that is going to cut the high frequency, so removing the noise. All right, this is exactly what we do here. The only difference is that I'm not going to engraft the filters. I'm going to learn by backpropagation the best possible filters for the task. Okay? So you do that. Now the issue is the number of parameters is huge. It's going to be the number of nodes. So if you have Facebook, n is going to be billions, right? So you don't want to learn a billion parameters, is too much. So what you're going to do is that you're going to parameterize your spectral function with just a few numbers of basis functions. And then the question is, what is the basis function? So if you use Chebyshev function, the one that we used, which is very natural in numerical analysis, basically you can reduce the complexity to k, the number of Chebyshev functions. And k is usually 16, 32. Okay, so it's very, very small. Okay, so at the end you have this. Now, so we published the paper in 2016. Then Thomas Keefe and Max Welling published another paper in 2017. And what they did is basically they did a first order approximation of Chebyshev, the paper that we have. Okay, and they have this GCN. How many of you know about GCN? Okay, this is why I'm very jealous. Because their paper is much, much more popular than our paper, because nobody understands our paper. So what they did is basically the first order. This is what basically this is what you should do. Okay, so you have a very complex theory. At the end, you make it linear, but you put the nonlinear part in the appendix. So this way, you know, everything is good. But anyway, so they are good friends. It's just a joke. So Thomas, Keith, so Maxwell, so they have this, and this is now the most popular, the most used GCN. Okay. Oops, yeah. Okay, anisotropic GNNs. So remember what I said. A grid, it has orientations. So orientations are very important. For example, images, we have a lot of information coming from, edges, textures. So it's something we need for a graph. So the next class of GNNs was basically to introduce back the orientation. The orientation is, for example, very important if you have two nodes in two different classes. I don't know if you do sports. There will be for related to tennis, that will be related to soccer, whatever. So you really want to have pattern matching differently for different nodes, which are not in the same class of information. Okay. So the first thing we did was actually gated GCN. So gated GCN is basically a PDE. So during my PhD, I work a lot on that. So you have images, you want to remove the noise, but you want also to preserve basically the discontinuity. So to this, what you're going to do is that you're going to diffuse, but on the edge, you are going to stop the diffusion. Okay? So we want to do exactly the same, but we want to learn it. We don't know where are the edges. We don't know at all. So we can learn everything now with as long as you have a data set, a loss, you can learn anything. So this is what we did. At the same time, the same year, so that was the paper introduced GAT, Graph Attention Network, by Peter Velikovic and Yoshua Bengio. And again, I'm very jealous. So in this paper, basically, this paper is it's the second most cited paper in our field. This paper has only, I don't remember, maybe 200 citations. So, but this paper is much better in terms of performance. But the story, this is where I think is very important for you to know, is that you should never be, Christophe Colomb. Okay, you should be the guys after. So the first paper is never the most popular one. You really need to understand what the community, how the community understand the story and change the story. So now what we do basically is that we have the paper, technical, and then we write a blog post. Because it's much easier for everybody to understand. You have picture, generated by ChatGPT, whatever. Everybody like it, and it's much more, understandable. Okay, so this is also one trick you should do. You have your paper, but you also have a blog post that explain in lay word basically what you do. I think this is, this is today a good trick. Okay, so these models, so GAT and this one, actually they have the problem of low expressivity. Low expressivity, you know what it means? Some of you know what it means, low expressivity. What does it mean a function is not very expressive? It means exactly what it means. So it means basically it cannot represent too much, functions. So if you have a complex, if you have very easy input data, linear is probably enough. You don't need to have too much expressivity, or low expressivity would be enough. Now, if you have very complex stuff like molecules, proteins, you really need a high expressive functions. So it is able to represent a large class of functions. Okay. So these models are not. Okay. Do you see why, by the way? Did I solve the problem of position? Okay. So a position is a unique identity of your node. If you take an image, the pixels, each pixel has a unique identity, which is going to be the same in any image you're going to take. If you have different graphs, different molecules, did I solve the identity problem? No, I didn't solve it. And this is why you have a low expressivity, because the model is not able to understand, if he is located here or located here. Everything is the same for him. So he has a lot of ambiguity, a lot of confusion. Does it make sense? Yes, thank you. The other thing is the overquestioning issue. Okay, so probably some of you learned about oversquashing, yes? Oversmoothing? Yes, some of you. Don't be shy. Okay, okay. Oversmoothing is not an issue. Michael Bronstein is not there, so I can say that. He has many papers on that. I don't think this is an issue. It's not something which is practical, something which is theoretical, but not, yeah. Don't record that. But oversquashing is a big issue. That's probably the most important issue. Okay. So the explosivity here is standard examples we use. So if you have this molecule, what your GNN is going to do is that it's going first to represent each node by one vector, and at the end you're going to have aggregation equation, something like the mean operation, and you get one vector. So you're going to map this graph into a k-dimensional space. Okay. If your GNN, your function represented by your GNN, is not expressive enough, what will happen is that two graphs, which are close to each other but still different, they can be represented, by the same vector. So you lose the ability to distinguish different graphs. And this is very important, of course. You don't want to give the same energy to your two graphs. Okay. So this is something that has been identified. And the first way to solve this problem was using graph isomorphism. Oh, it's already 12. Okay. Yeah. Okay. Yeah. Oh my God, we are slide 10. Okay. So so isomorphism just means basically, so you have this molecular graph here. You see, you have an atom of carbon, hydrogen, and you have an indexing, which is arbitrary, completely arbitrary. Okay. So here I give you a second molecular graph. Okay. Hydrogen, oxygen, and also this indexing. They look like different. They are exactly the same. Because you can find a mapping between this indexing here and this indexing here that will preserve the neighbors. So they are exactly the same. So this is a big issue because if you have a neural network, a graph neural network that is not able to distinguish that, or saying they are the same, so it will never be able to generalize. Okay, so this is a very simple stuff. So Westphaler-Lehmann, in a long time ago, in '68, as you can see here, they provided a very simple test, which is called a coloring test. So what you do is basically you start with some colors for each atoms, and then you update the colors by just using the atom and the neighbors. So you create a new color. By doing that, you have this process that you can see here. At some point, it will stop very quickly, actually. And you can look at the histogram of colors that was created. You can do that for these two different graphs, and they will have the same histogram of colors. Okay. So it seems that, yes, it's true. I mean, they are isomorphic to each other, so they should have the same histogram of colors. However, this test is also very weak. It's not working very well. So if you have these two molecules here and here, they will produce the same histogram of colors, but they are different. Okay. So this test is actually not very powerful. So people say, okay, the issue is that we don't have enough color. So let's find a process to increase the number of colors. Okay. And they developed these Westphaler-Lehmann GNNs. This is called, so they have this KWL test. So I don't want to go too much into the details because it's not something which today we use. It's really theoretical. And again, I'm losing people, so I need to be on track. So, but the complexity is very high. So if n is your number of nodes, k is going to be the tuple of nodes you're going to use to compute the colors. So before, I only used two tuples, so the node and its neighbor. But I can use more. I can use 3, 4, 5, and I will produce much more colors this way. So this technique was de facto the most expressive GNN for some time. And it was used basically to improve the expressivity of GNN. So having functions which are highly expressive. So if you have a complex input data, like a molecular graph or a protein, then you are going to represent this function, this data very well. The problem is it's too expensive in terms of memory and also in terms of speed. And the other thing that we notice is actually high expressivity. If you have high expressive functions, does it mean that you have generalization, high generalization performance? No. So a function which is highly expressive doesn't imply to be, doesn't imply that it's going to generalize well. Can you give me one example of very simple but highly expressive function which doesn't generalize well? Sorry? Speak up. What is the function which is the most expressive today? Transformer? No. Convolutional neural networks? No. I don't hear, I'm sorry. Regression? It's feed forward. MLP, multi-layer perceptron. Okay, if you have a network with 2 linear layers, you can use the universal theorem, and you can basically express any function, any continuous function. So this is the most expressive function on the market. But nobody used that. It doesn't generalize. It's the worst generalizer. Okay, because you need inductive bias. Okay, and you need an inductive bias which is not too strong, okay, and not too weak. So for a long time, convolution was basically what we needed. Recently, we understood that the attention mechanism is exactly the right inductive bias, not too strong, not too weak. That's super important. Do you agree with me? Yes? Okay. All right. So there was a lines of paper, a series of papers on this WHGNN. And what we decided to do is say, oh, actually, at the end of the day, what you want is to get a unique identity to your node, like you would do it for images, for the pixel in your images. Okay. And there was some initial theoretical result that show precisely that if you have a unique identity, so this is a position, now we call it positional encoding for each node, then you will be able to be more expressive, basically. So we follow this direction, this theoretical direction. So, so what is the simplest positional encoding you can do for a graph using the index, right? So each index, so this is index 1, index 4, index 9, and so on. This gives you a unique identity for each node. Okay, you are able to disintegrate 2 nodes this way. The problem is, you remember that your function must be equivariant with respect to the permutation. Okay, so if I change the indexing, I still want the same representation of my GNN. Okay, so if I do that, I will need to consider the n factorial permutation during training. So you know that when n is larger than 100, it is over, right? So there is no computer that can do that. Okay. So what are the properties we try to identify for designing a good positional encoding? So you want uniqueness, that's for sure. You want something unique, so your graph neural network will be able to disintegrate different nodes. You want the permutation invariance. So if you take the same graph, you change the indexing, you still want the same GNN output. And also you want distance sensitive. So basically, if you have 2 nodes which are close to each other, we would like the positional encoding to be close to each other. And if the 2 nodes are far from each other, we want them to be as different as possible. Okay. So doing that, there is something that works very well, which are the Laplacian eigenvectors. So it's a very old technique. The idea is you take your graph, and then you project your graph in a Euclidean space. Okay, so what it means basically, if you have 2 nodes on your graph which are close to each other, when you project, for example, in 1D, just one line, you want your 2 nodes projected to be close to each other. And if your nodes are far away on the graph, you want the distance on the line to be far away for the two nodes. Okay? So this has everything. Unique representation. It's also distance sensitive. So the positional encoding between two nodes depends on how far they are on the graph. And there is something also very interesting is that, so if you know transformer, so do you know that transformer is also equivariant with respect to the permutation of the words? Is it true or is it not? Is it true?
Without positional encoding, yes.
Exactly. But I don't consider the positional encoding. If you have transformer without positional encoding, then the ordering of your words, you don't care. You know about this, right? So a transformer is basically like a GNN. Okay? So what we do in text, we add this positional encoding, for example, the order of the words, 0, 1, 2, 3, and so on. Or we add, do you remember the cosine and sine function? Okay? So what they do, the cosine and the sine function, this is actually the eigenvectors of the line. If you take the line graph, you compute the eigenvectors, you will have the cosine and the sine positional encoding of the transformer. You know about this, right? So basically it means that if you compute the Euclidean distance between two vectors of positional encoding at, let's say the word 0 and the word 100, or let's say that you increase the distance, so it will continuously increase. Okay? So we do the same here. The only difference is that instead of considering the line graph, we are considering arbitrary graph. We don't care. Any arbitrary graph is okay. Okay. Okay, let me finish that and then we decide what we do. Okay, so there is still a limitation with this Laplacian positional encoding. It's not perfect. So you know that what we do, we are doing a factorization of the Laplacian. Okay, we have U transpose U in some sense. So U are the eigenvectors. So it is a quadratic, right? It is quadratic. So you do the eigenvector square. So in this situation, you have an ambiguity because when you compute the eigenvector, it can be plus or it can be minus. Because it's quadratic, you always multiply everything. Okay? So there is this ambiguity, which is basically we don't know which is the correct sign. So during training, what we need to do is to randomly swap the sign of the eigenvectors. So usually the number of eigenvectors is not very large, something like 8. It's enough. So we need to do 2 to the power 8. Of course, we do it randomly. And so it's not mathematically perfect, okay? But in practice, it works very well. So this is the magic of deep learning, we don't know. So today, we don't know actually if there exists a positional encoding for graph which satisfy all properties of unique node representation, equivariant with respect to the ordering of the indexing, and distance sensitive. We haven't found any of that. Okay, so I doubt actually there is a mathematical solution to this, but prove me wrong. Okay, so there are different ways to do positional encoding. I think Vijay, I discussed with him yesterday, he introduced also to you different positional encoding. The other one that we did was a random walk, just to tell you that there are many ways. You can do your own positional encoding depending on the problem that you have. Okay, so for example, for social graphs, I think the Laplacian positional encoding is good. Now, if you do molecule, the best positional encoding are actually the shortest distance between the atom in the molecule. I don't know why. It's just in practice. Okay. So different ways to do that. Okay. What do we do? I can take some questions here, and then we can stop. So I will also be the lecturer at the next section. We can start again. It's up to you because I don't want to be between you and lunch. So Or I can keep going. Probably not, because that's the right time. It's up to you. What do you want?
So why are we not using?
Okay, so let's have questions.
Why are we not using rotationally positional embeddings for graphs? So we can use some sort of a
Yes.
spectral distance.
Absolutely. So yes, this is something when some of you do not know rotationally positional encoding. Everyone knows? Shall I explain a little bit? Okay. So when transformer came, so as we noticed, transformer is independent of the ordering of the words. So you need to add positional encoding to know that this is the first word, second word, third word, and so on, because there is the causality information in language, right? So the first thing people did was very simple. Okay, let's have the positional encoding 0, 1, 2, 3. They are just integer, and then you do an embedding, a linear embedding. Okay, simple. The problem is that if you, during training, you have a length which is not in the test set, it's not going to work. So what people decided to do is to do the cosine and sine positional encoding, because it's a continuous representation, and even if you don't have the length in your training set, but in the test set, it's going to work in any way. Now the problem of this absolute positional encoding, 0, 1, 2, 3, and so on, is that if you have the same sequence of words, but you translate it, you're not going to have the same output of your transformer. You see why? Because here you have 0, 1, 2, 3. It's going to give you some embedding depending on 0, 1, 2, 3. And if you put it 10, 11, 12, 13, it's going to have different also positional encoding value. So the output will not be the same, not because of the word embedding, but because of the positional encoding. So what people say, okay, let's do positional encoding which are translation invariant. And they develop rotationally positional encoding. How do you do shift invariance positional encoding? You use the dot product. Simpler. The paper is very hard to read, but at the end you just do dot product. So rotary positional, to come back to the question, yes, you can do rotary positional encoding for graph. So basically you will have you will have a relative distance between the nodes. So I tried it, I implemented it, the performance is not as good. So you can do it, but it's not working well.
Any intuitions why, sir?
I don't know. That's a good question. So help me, please. Any other questions? Please. Let's have that. Everyone can hear.
When we are using the eigenvector-based encoding for position, why is it guaranteed that nearby nodes in the graph will have smaller distances in that embedding?
Say it again.
We are using eigenvector-based encoding for position, right? So in that case, why are nearby nodes guaranteed to get a similar encoding for position in the graph?
Sorry, I don't understand. Someone can? What was the question? I'm sorry, I don't understand the question.
I mean, when you introduce that, we need to have a position encoding where the closer nodes are closer.
Yes.
And then we took the Laplacian position encoding. There, the way we encoded it was the sine and cosine functions. But what was the guarantee that the nodes which were closer are actually closer?
Oh yeah, that's a very good question. So thank you. Sorry, I understand now. So it's basically the way you build, So you have your graph, and what you do is that you project your graph in a k Euclidean space. So let's say that we just have one line, okay? Just have one line. So doing that is actually minimizing the Dirichlet energy. Okay, I don't want to go into the detail. So basically, if you have 2 points which are close to each other on the graph, when you compute the eigenvectors, this will give you the minimum energy if your 2 points stay close to each other. I have some equations I can show you. No, not here, but I can show you some equations. So it's mathematically very easy to see it. Okay, so we can talk offline. I will explain you. But basically, this is by construction. When you want to project a graph into a k Euclidean space, you preserve the distance. And basically, so some of you know about dimensionality reduction. Yes. So linear and nonlinear dimensionality reduction use exactly the same hypothesis. Every 2 points which are close to each other in a high dimensional space, they're going to stay close in the low dimensional space by dimensionality reduction. This is the first condition when you develop a technique. And then you had other properties, but this is the first condition. But I can show you with the Laplacian. It's very easy. I need something to write. Any other question, or we go to lunch?
It's not time for lunch yet. I think it's until normally 1 p.m.
Okay, but we can make a break. I mean, it's up to you. Or I can keep going. It's up to you. But I know it's maybe not the right time. It's up to you. Shall I continue? Yes. Wow. Okay. Good. Okay. Okay. So let's 25. Okay. Let's try to do 15 minutes, and then we have more questions. And you tell me. I mean, if you want to stop. Again, I'm going to be there at the next session, boring you. So. Okay, so let me talk quickly about the transformer. I already mentioned quite a bit. So the problem, so why we developed, so you probably know about the revolution. So we started with computer vision, right? So there was convolutional neural networks. Suddenly it changed everything in computer vision. I remember some of my professors were very angry about this. They say, oh, we have to change everything. Yes, but it's just science. But then it took a long time, you know, for natural language processing, because yes, we can do convolutional neural network for sequence. You agree with me? We can do convolutional neural network for sequence, right? No? Can we do convolutional neural network for sequences? Yes. 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 Yeah, we can do that. There is no problem. So it's just, you know, we have a pattern, let's say of, I don't know, 5 words, and then we shift along the sequence and we compute activation this way. Okay, so we can do that, but it was never as good than vision, never. Okay, why? I don't know. So people starting looking at recurrent neural network, and there was one that was developed in the 90s, which was LSTM, long short-term memory. Okay, so this one, because we didn't have any transformer at that time, so this one was by de facto the one that we used to represent sequences. So remember what I said before is that why it is, the theory is nice. I love the theory. It's a nightmare to implement and to stabilize. So basically, again, you can summarize the sequence by one vector, because you have this recurrence equation. The recurrence equation takes as an input the summary of the sequence so far plus the new word, okay? And it updates the summary of the sequence. And it can do it, you know, at infinity, okay? So it looks like when the first time I read the paper, I think, oh, this is a great idea. The problem is then you look at a little more precisely, and you see that, oh, this is actually something that we know very well. This is a dynamic system. Okay, it's some kind of Markov, you know, random process, which is here. But it's better because we don't have to decide the coefficient. We actually can learn them by backpropagation. So it looks like a great idea. Okay. The problem is there is a lot of nonlinearity. Okay. So remember that if you stack, what happens if you stack 2 linear layers? It's the same as having only 1 linear layer in expressivity. So if you want to use deep learning, you need to add some nonlinearity. Okay, so you use ReLU or the recent one, I don't know. But when you do that, you introduce nonlinearity. And then you have a dynamic process which becomes nonlinear. And you know what happens when you have nonlinear dynamic process. You have instability, you have chaos. Yes? So these systems, on paper, they are fantastic. When you start coding them, it's a nightmare. So for me, it was very hard to actually be convinced that this LSTM will be there for a long time. Because deep learning, it has this paradox that it's the model that are the simplest one, they are actually the winners. So you cannot scale up very complex model like LSTM. You cannot do more than 2 or 3 layers. You cannot do 100 layers because they are so complex that the system, the chaos, the dynamic will change very quickly, and nothing is going to be learned this way. So any small perturbation can amplify or can vanish. And the other thing also is that backpropagation. So when you do backpropagation, you know that because of the recurrence equation, you cannot do that in parallel. You need to go through each word. So the forward pass will go to each word if you have 1 million words, and then the forward pass, the backward pass will go back to this 1 million words. It means you cannot do it in parallel. When you have large-scale data set, if you don't have an architecture that you can implement in parallel, bets are off. Okay. So is transformer parallelize? Can you parallelize transformer? Yes. Yes, exactly. You can parallelize transformer. Okay. So this is why also it's very nice. And the last thing actually that we observe is even if you use RNN, let me go there. So this is the performance of translation. The higher, the better. Okay. And here, this is the sequence length. Okay. So what you see, this is in dashed. Basically, this is the standard LSTM. If you increase the length of the sequence, everything is fine if you have 20 words. But then if you have more than 20 words, you see the performance decreases very quickly. And again, this is due to the vanishing gradient problem. So it means basically that, and we know that for quite some time, you cannot learn more than 50 words of dependencies. So if I say something, I am French, blah, 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 more than 50 words, and I say, what is my citizenship? Then LSTM will never remember I was French, and will never be able to answer. Okay, so this is called the long-range dependency of your system. You want to be as long as possible. Okay. So over-squashing, this is, I think, the most important problem in GNNs, and I'm going to tell you why. So remember, so any neural network is a message passing. Okay, so this is the node I, so it can be a pixel, it can be a word in your sequence, it can be a node in your graph. It's a vector, right? HI is a vector, and you are at the next layer. So you want to update the node representation. And for this, you are going to use the node representation of, okay, the same, but at the previous layer, at the current layer. And then you are going to use the neighbors. Okay? So if you are using an image with convolutional neural networks, basically the neighbors are just, so you have, you have the center pixel, and then you have a patch around it, like 3 by 3 pixels. Okay? And you are going to use basically the colors of this 3 by 3 pixel around it to update the value of I, okay, at the next layer. For RNN, for the sequence, you are just using the previous representation of the sequence. Okay, that's it. For the graph, you are going to use the topology of the graph. Okay, so what are the neighbors, basically. But in any case, that's always the same equation. Okay, so what it means that if you want to propagate the information from this node to this node here, and there are maybe, let's say, 20 nodes between, how many layers do you need? $100? 2? At least 20. Okay, because at each layer, what you do, you are increasing the restriction field by 1 hop, and 1 hop only. So if you want to get to, if you have 20 nodes, you need at least 20 layers to get there. Okay? The same for the graph. For a graph has a diameter. Okay? Basically, if you want to get to this point here, you will need at least, let's say, maybe, again, 30 layers to propagate the information from here to here. And this is only for the task that requires long-range dependency. Okay, some tasks are very simple. You just need to know the neighbors. Okay. So when you are using CNN, the local reception field is going to increase quadratically with L squared because we are in 2 dimensions. Okay. For the sequence, is going to increase linearly with respect to the length of the sequence L. Okay. Now, if you take GNN, for example, here I just take a binary graph, then this is going to increase exponentially. Okay. So what it means that to update the current representation of my node, if I'm using a CNN, I'm going to use L squared number of vectors. Okay. For RNN, I'm going to use L number of vectors. For GNN, I'm going to use exponentially 2 to the power L number of vectors. So usually, most of the vectors, they are just not useful for the prediction. So they are noise. Only a few vectors are important. But what it means that you ask your GNN to understand what are the important vectors, and only a few are important, 1% are important, and 99% are actually just noise. So this is very, very hard, okay, for the system to do that. So we know that for the reverse squashing is, of course, as I said, something which is true for any neural networks. So for RNN, there was a huge issue when you wanted to summarize a book. You know, a book has 50,000 words. RNN was not able to do that. Remember, only 50. The long-range dependency was only 50 words compared to 50,000. Okay. So this is exactly what happened. Is suddenly people not at Google, by the way. So when you are not at Google, you cannot use a lot of GPUs to run experiments. You have to use your brain. So someone very smart at Mila basically say, okay, I'm going to add a new mechanism on the top of RNN so I can communicate between long-range nodes. This mechanism made the attention, the softmax attention, and he was rewarded this year, I think, at ICLEA, one of the Test of Time Award. Okay, so this is Badano, okay, and Yoshua Bengio and Cho. So for RNN, this is hard, but for GNN, this is even harder, okay, because of the exponential number of vectors. Okay, so the problem with transformer, so transformer looks like, you know, it can solve the problem on paper because you have the attention. The attention mechanism basically makes that if you have a sequence of L words, each word is going to communicate with all the words in the sequence. So to get the right prediction, you need to communicate the first word with the last word. You can do that in one layer. Okay, in one layer you can get the answer. So suddenly you solve the problem of long-range dependency. It doesn't solve the problem of reasoning, but it solves the problem of long-range dependency. I can go back to the reasoning part if you want. But to do that, you need to compute something. You need to compute the similarity between your word representation, so they are just vectors. And to do that, you need to compute the dot product between the word representation and itself in some sense. There are some learnable parameters, but it's not important. If you have L number of words in your sequence, the complexity is going to be L squared. Okay, computing the pairwise dot product between all words of d dimension is n squared times d. It's huge. So for me, it was always a mystery that Google say, okay, let's go with that because Google is the king of linear approximation. Because you need products, right? So if you have something which is quadratic, they will never like it. If some of you have done some, preparation of Google, interview, the question is, how do you make your algorithm linear? So when I saw the quadratic complexity, I was very surprised. Okay, but I mean, they found a way to convince their manager to do it. Anyway, so this is fantastic because suddenly, now we are, so some of you know Word2Vec. So Word2Vec was basically the precursor. So you have, you take internet, whatever, and then you represent, this vector, this word, by looking at the neighbors. Okay, so you do that, and then you're going to have a vector representation of each word. The problem is that it's completely static. So if you change the context, you will not be able to change the representation of your word. And this is very important. Language depends on the context. So for example, I have always the same example. If you want to represent the word broke, so the vector representation of broke, it must change depending on the context. For example, the vase broke, the news broke, Sandy broke the law, and so on. So you need to change the representation of the vector if you want to make the right prediction. Okay? You can do that with this attention mechanism. Okay. Okay, maybe last thing before I let you ask questions. So as I told you that now you can communicate between words in one layer of transformer. Why do we need 100 layers of transformer then? Because in one hop, in one layer, you can do one jump. Why do you need more? Exactly. And this is also related to reasoning. So how does it work? How transformer works and why it's so revolutionary, actually. So transformer is just word matching, but a sequence of word matching. So for example, if you say, okay, so okay, I got the bottle of milk. Then I went to the bathroom. Then I go to watch TV. Then I go to say hello to my friend. Where is the bottle of milk? Okay. To do that, you need to do some pairwise matching, okay, between this sequence to get to the milk is actually in the restroom. Okay. So if you, of course, if you overfit, you will get in one hop. But overfitting will never give you reasoning. So by forcing the system to have a trajectory of word matching to get to the solution, you force the system to reason. Reason in a weak sense. Okay? But this is how it works for transformer. You have a trajectory of activations in the 100 layers of transformer to get to the solution. And this is why it's so powerful. But we cannot get more than this. I think it would be, I mean, this is a debate. I don't know. All right, so any question, please, before we stop? We make a break. Yes, please. Well, let's have a microphone so everyone can hear.
Does the pairwise matching actually happens?
Happens?
Yeah.
Yes. They happens here. So here you have basically the dot product. You have the dot product between, so Q is a sequence of L words. Each word has a D-dimensional representation. When you do Q times K transpose, you are basically doing n square matrix. And this is basically how strongly they are connected, how the words are strongly connected. Okay? So if two words are strongly connected, they will be used to update the representation of the word. Okay? So this is where you have the matching. The pairwise matching is done here. But I told you, one pairwise matching can jump you anywhere in the sequence. It doesn't give you reasoning. What gives you reasoning in this sense is basically a sequence of jumps that understand how you get there. And this is why they are so powerful, I think, today. But this is, yeah, if this was your question, I hope, yes, I answered. Thank you. Any question is good.
Sir, I could not understand why a larger or an exponential chapter field for graph neural nets is bad.
Oh, yeah.
Because in logarithmic, see, we have n nodes, then in logarithm of n, log of n, we can cover everything.
Log of n of what?
So see, we have the diameter is n of the graph.
So when you update in any neural network, you agree with me that when you update the representation of a word, of a pixel, of a token, whatever, you are going to do that, right?
Yes.
Okay, you agree with me. So now the question is, what's the size of the neighborhood, right? If you agree with me, here this is the neighborhood of I. So this is, the question is, what's the size? How many vectors we have to update the representation of the node I? Everything boils down to the size, okay? So if you take a sequence, the size is just going to be, it's easy, right? It's just the number of nodes that you need. For a graph, what happens is that each time you stack one GNN layer, you are considering all the neighbors. So, but you do that more and more. So that's why I have this picture here, right? If I am here, so this is the first GNN layer. This is the second one. This is the third one. You see, each time I'm just increasing a lot the reception field. So the problem is, usually when we need to make a prediction, we don't need to have a lot of information. So of course, it will depend on the task that you want to solve. But for the majority of tasks, you don't need too much information. Actually, to make the right prediction, maybe you just need to have this one, and that's it. That's the only thing you need. Everything else will be there and will act as a noise.
Yes, so now for example, that we take the same graph and in 3 layers we are able to cover the entire graph.
Yes.
We are able to filter out everything that we want to know in just 3 layers. If see we were using some sort of a CNN, maybe in a grid sense or something, then in that case we would require many more layers to discuss the same amount. So I am still not able to understand why GNNs are worse, or I'm not able to understand.
Okay. So if you are using a CNN, okay, if you are using a CNN, exactly, you will have the same issue. So each time you increase by L squared, okay? So I think, yeah, this is a very important point. So, and thank you for the question. So yes, the oversquashing is one issue. It's not the only one, okay? So here, yes, you're right. So for the CNN, if after maybe 20 layers, you will cover the entire image, okay? This is probably what you're going to do. But still, people do 100 layers. The 100 layers come from the reasoning part. Why do we need to do 100 layers? Is for the reasoning part. Now, why it works is also more structured. There is also a question of structure of the function, which is better for convolutional neural network than it is for GNN, because GNN is heterogeneous.
I'm sorry, but can you please go a little slowly? I'm having a hard time deciphering.
Yes. So the reception field is only one part of the problem, okay? So there are many other parts of the problem. So maybe I'm just going to repeat. So let's do it offline, so everybody can yeah, ask another question and or maybe go to lunch.
So I've heard, I've read that message passing GNNs, they struggle with long-range dependencies. So are there any theoretical results where message passing GNNs, fail, there is graph transformers succeed? Like what kind of position
Okay. If I understood the question, so you say that some GNNs have issue with long-range dependency, right? So why graph transformers solve the issue?
Yes, like are there any non-theoretical results where they have solved the issues rather than consistency?
Yes, so this is an active research area. So for example, Michael Bronstein, he has some direction to solve the issue. This is called rewiring. I don't know if he mentioned that rewiring. So basically, the idea is you may add artificially some long-range connection between two nodes of your graph to solve your problem. So this is one way to do that. Graph transformer has two versions. I will talk about this after lunch this afternoon. So you can do a sparse representation, or you can do also a dense representation, so where you have long-range dependency. But let me answer more precisely to this question this afternoon. But yes, there are many papers, theoretical, trying to understand over squashing, yes, and long-range dependency. All right, guys, so let's have a break and see you this afternoon.